Welcome back. In this video, we are covering some powerful algorithmic tools that go beyond sorting and searching. We will explore string matching techniques, optimization strategies like linear programming and network flows, and wrap up with computational complexity, including what makes a problem truly difficult. Let's dive in. First up, string matching. You are given a long text and a shorter pattern, and your goal is to find every position where the pattern appears in the text. The naive method checks every possible position where the pattern appears in the text. It is simple but slow. Time complexity is nm, where n is the length of text and m is the length of pattern. Improve efficiency, we use smarter algorithms. This algorithm compares from right to left and skips ahead using mismatch info. This treats strings as numbers and compares hashes. It is fast on average but may need verification. This methods build a machine which tracks prefix matches. And this algorithm recomputes a fail function to avoid rechecking, giving us linear time matching. Data structures trees. Trees are like trees that store words efficiently. Each node represents a letter, and paths from root to leaf represent complete words. They help us check if a word exists, count substring occurrences, and even find the longest repeated substring, all with fast lookups. Regular expressions describe patterns in strings like starts with A, ends with Z. Every regular expression corresponds to a finite automation and vice versa. This connection lets us extend string matching to pattern matching. Python's built in libraries make it easy to implement these ideas in practice. Now, let's talk about optimization. Imagine you are producing burfis and halwa. Burfis earn rupees 100 per box, while halwa earns rupees 600. You have demand limits and total production capacity of 400 boxes. The goal is to maximize profit. So 100 boxes plus 100 burfis plus 600 halwas can be written as 100b plus 600h, right? So we start at a vertex of the feasible region, then move to adjacent vertices that improve profit and stop where no further improvement is possible. So the feasible region is convex. Sometimes the problem has no solution, that's infeasible. Other times the solution can grow infinitely, that's unbounded. The key is that both the constraints and the objective functions are linear, like a1 x1 plus a2 x2 less than equal to k. Network flows model problems like routing or resource allocation. We have a directed graph with capacities on edges and two special nodes, source and sink. Flow must respect capacity and be conserved at every node except source and sink. This algorithm starts with zero flow, finds unsaturated paths, and augments flow. It uses a residual graph to track remaining capacity and reverse edges. BFS helps find shortest augmenting paths. If our initial flow choice is poor, then reverse edges lets us fix them. That's the beauty of residual graphs. They allow corrections and flexibility. Now reductions. So reductions help us connect problems. If problem A reduces to problem B and B has efficient solution, then A does too. For example, bipartite matching reduces to maximum flow and maximum flow reduces to linear programming. But if A is intraceable and reduces to B, then B is also intraceable. So reductions help us classify problems by difficulty. Sometimes we don't need to solve a problem. Just check if a proposed solution is valid. That's what checking algorithms do. For example, in factorization, input is a large number n. Certificate is two numbers p and q such that p into q is n. So checking just means verifying the multiplication. So this idea implies to problems like satisfiability, traveling salesman, vertex cover, and more. Now let's wrap up with complexity classes. We solve problems are solvable in polynomial time. NP, the problems where solutions can be checked in polynomial time, while NP complete is the hardest problems in NP. If we solve one efficiently, we can solve all NP problems efficiently. These classes help us understand which problems are easy, which are hard, and which are possibly unsolvable in reasonable time. To summarize, string matching has multiple efficient algorithms balancing pre-processing and runtime. Tries and automa- Tries and automata help with pattern storage and matching. Linear programming solves optimization problems with geometric intuition. Network flows handle capacity constrained routing, while reductions connect problems and reveal complexity. Checking algorithms and NP complete problems help us understand computational hardness. Thanks for watching, and if you found this helpful, don't forget to like, share, and subscribe for more algorithmic deep dives.